Listen to the hum of a heavy manufacturing floor, and you are hearing the pulse of modern industry. The scale and torque of these rotating machines are what make global infrastructure possible. If you study electrical engineering, you are taught that the machines powering this grid fall into 4 distinct categories. One semester on static transformers, another on DC motors, then on to AC induction and synchronous generators. It feels like learning 4 different branches of physics. That separation is an illusion. There are not 4 separate sets of laws governing the power grid. There is only one underlying mathematical framework at work here. To see it, we have to look back to the 19th century and the foundational axioms of electromagnetism discovered by Michael Faraday. He proved mathematically that changing magnetic flux induces a voltage. Once you accept that single premise, the perceived differences between alternating current, direct current, and static transformers disappear. The physics never changes. The only thing that changes are the mechanical constraints we place on the hardware. To master the grid, we have to stop looking at a multiplicity of isolated devices and understand the single universal machine that governs them all. Every rotating machine shares a universal architecture, a stationary outer stator, and an inner rotating rotor. Inside are coils of copper wire carrying current. The final ingredient is the invisible magnetic flux linking them across the air gap, the bridge transferring energy. The crucial third ingredient is relative motion between those windings. Whether the rotor is locked in place or spinning at thousands of RPMs dictates exactly how that magnetic coupling behaves over time. This theoretical construct, windings, magnetic coupling, and relative motion, is known as the Kron primitive machine. By starting with this single physical template and simply adjusting the constraints on motion, an engineer can construct and predict the behavior of literally any electrical machine ever built. Let's build the first variation. We take our 2 coupled windings and strictly enforce 0 relative motion between them. The inner core is locked. This 0 motion configuration gives us the workhorse of the power grid, the static AC power transformer. Because there is 0 motion, the changing magnetic flux can step voltages up or down to transmit power across vast distances, but it converts exactly 0 electrical energy into mechanical power. Now we change the parameters. We unlock that inner core and allow the rotor to spin freely inside the magnetic field. This creates the induction machine. For the changing magnetic field to induce a rotor current, the rotor must spin slower than the AC magnetic field itself. It has to slip behind. This chart plots torque against rotor slip, showing the machine's ability to generate torque under load. The absolute peak is the breakdown torque. If a heavy load forces the machine past this point, the magnetic coupling collapses and the motor stalls. The static transformer and the spinning induction motor rely on the exact same magnetic induction. Only the physical freedom to slip separates their identities. We can alter the machine's constraints again. If we inject a direct current directly into the rotor, the magnetic poles lock together. The slip is forced to 0. This 0 slip state is the synchronous machine. It spins in perfect lockstep with the grid and is responsible for maintaining the exact 50 or 60 Hz frequency of global power systems. This chart shows the power angle curve of a synchronous machine. With slip locked at 0, stability is dictated entirely by the phase angle between rotor and grid. Push the rotor past the 90-degree peak, and you lose synchronization entirely. We apply a final constraint, a physical switching device on the shaft. This is the commutator. As the rotor spins, internal currents alternate. The commutator acts as a mechanical linearizer, forcing those alternating currents to exit as steady direct current. This mechanical action directly informs the foundational EMF equation used to calculate voltage in all DC machines, tying the physical rotation to the exact magnetic flux cut by the conductors. Whether you magnetically lock the slip to the grid in a synchronous generator or mechanically rectify it with brushes in a DC motor, you are simply manipulating the internal frequencies of the Kron primitive machine. These physical variations are unified by one mathematical framework. This dynamic matrix equation calculates voltage, current, and power. The first two terms account for resistive heat loss and magnetic field energy. The final variable is the rotational coupling matrix multiplied by rotor speed. This specific mathematical term is the only place where electrical energy converts into mechanical torque. We can test this. If the rotational speed variable is 0, the math proves the mechanical power conversion is exactly 0. This describes the stationary transformer. This single matrix equation safely replaces dozens of disparate formulas scattered across engineering textbooks. It scales seamlessly from a stationary transformer to a spinning DC traction motor. Abstract mathematics must eventually survive the factory floor. These machines operate in heavy industrial environments where they degrade over time. The physical reality of power flow dictates that not all the electrical power entering the machine exits the shaft as useful mechanical torque. There are internal losses. The resistive heat loss variable from our universal matrix maps directly to standard copper loss equations engineers use to audit machines. Analyzing the ratio of output to input power uncovers a counterintuitive engineering truth about how these machines operate. This illustrates the efficiency curve. Absolute peak efficiency only occurs exactly where fixed mechanical losses match the variable copper heat losses. Because of this, peak efficiency is almost never located at 100% full rated load. It hits peak efficiency earlier. Understanding the mathematical split of these losses lets engineers properly size machines for their specific loads. Guessing the size ignores this curve and guarantees massive, invisible energy waste across industrial grids. We also have to account for the violent starting dynamics predicted by our theoretical models. That requires heavy protective gear. Recall the induction motor's torque slip curve. The extreme high slip state at startup causes the machine to draw massive, dangerous current spikes from the grid just to break inertia. Standards bodies like NEMA classify machines into specific design classes based on these starting torque and current profiles to ensure safe deployment. Class A and B machines pull extreme inrush currents when starting. This reality forces engineers to strictly follow National Electrical Code sizing rules. The code mandates that protective conductors and breakers must be explicitly sized to handle 125% of the motor's full load current to prevent thermal failure. When this unified knowledge is applied correctly, the result is a perfectly sized, fully protected, and automated machine safely executing its mechanical duty. This unified framework transforms the way engineers approach the grid. By reducing every transformer and motor to its essential elements, it provides the tools to design, protect, and control the mechanical pulse of the modern world.